Everyone, my name is Zhu Feng. I'm doing this project presentation about my master MSc project neural networks-based personalized real-time visualization framework for hearing impact for enhancing music sensation using serverless computing. First of all, I suppose everyone heard about news like some museum made a special exhibit for the blind. This is kind of news that is commonly heard nowadays. But did anyone of us heard about a concert for the deaf? Not that often, right? According to the data from WHO, blind and deaf are nearly commonly happening in the world, and they both have significant negative effect on people's daily life. But if we have a search on Google about museum for the blind and concert for the deaf, this is what we got. We have 15 million searching results on museum for the blind in the past year, but we only get less than 1/3 searching results on concert for the deaf. This is the problem that more effort should be devoted to the hearing impact population. Music is an extremely common element in our daily life. We can hear music in a restaurant, in a shop, or even in a street. You can hear music everywhere. It's gonna be a great help in mental health care for the deaf to be able to sense the music just like the normal. Medical surgery implant is one of the solutions, but it gets several problems. First of all, it is really expensive, not affordable for everyone or every family. Secondly, it has a limitation on the cause of deafness. It can't cure deafness of all the reasons. Finally, it's a once-for-all deal. It can't adjust slow hearing degeneration, which will happen to every one of us along with the growth of age. So we need a cheap, highly universal and solution, and it should be a assisting tool, but not a replacing surgery. So that's why we need music visualization in this field. This problem has a lot of challenges. First of all, there is hardly any existing similar work. This field is really touched. The existing music visualization study more focus on transform existing MIDI file to a video, but not with a real-time microphone. And this appliance apparently requires really low latency, but it involves multiple threads, so it's also a challenge. In our work, we addressed several gaps. First of all, we realized a real-time music visualizer offering customized experience. And we merged a music emotion recognizing MER model in our framework so that the emotion information can be a supplement of the information loops during the visualization process. Finally, we choose serverless computing as the carrier of our framework so that it's going to be highly available regardless location and time as long as you get internet. In our work, we have several contributions to the field and to the society. First of all, with our framework, the hearing impact population can see the music anywhere, anytime with low to zero cost, just like the normal. The backstage database will store every record and the feedback emotion labels, constructing a dataset which can constantly improve the accuracy of this service by regularly retraining of the model and further benefits the whole MER study in the future. And also we proposed a new MER model structure significantly improve the accuracy of the prediction on small fixed length audio fragment. Then let's have a look how this framework works. This is the deployment framework of our proposed work. It starts with a endpoint device, like a cell phone, an iPad, a laptop. As long as it has a microphone and a screen, it can work with our framework. The microphone will collect the audio pieces from the outside environment and send HTTP request with the audio signal to the backstage, the cloud computing platform. And this signal will be processed and go back to the endpoint device by HTTP request to display the music on the screen. We used a user account management system with the Firestore so that everyone can build their own personalized music experience by setting the relationship between colors and emotions. And after every recording, the record and the feedback label will be stored in the Google Cloud storage. This is the framework inside the backstage. Everything starts from audio sensor. It will make signal data string pass to the signal processing thread. Then it will be two different threads that working in the backstage framework. One is MER thread and another is visualizer thread. The MER thread gets the signal and process it in three different ways and combine them to as the input of the model. The model will output emotion value and the emotion class, which can be seen on the left of the screen. We use a 5 emotion system: angry, excited, sad, relaxed, and natural. And we also use the 2 value system, the arousal and violence. Combine these, we can build our emotion information to supply the whole visualization process. With the visualizer, the pace and magnitude will be produced, and you combine with the emotion information in the music visualization system. After this, the emotion comment will be collected and stored in the backstage. Then let's have a closer look in our music emotion recognizing model. Our model can be roughly divided into 4 different stages. The first is a convolution neural network group. Consists of an array of CNN layer, convolutional layer, with different settings. They will provide a deep enough feature learning so that the audio signal can be concentrated into a few features to be passed to the next stage. Then a PC stage will work as a feature number reductor, where it will reduce the number of features and get rid of the redundant information so that the next layer can get a clear input with no distribution of redundant information. Then we use a recurrent neural network layer. Inside it we use a long short-term memory layer. They are very good at learning from sequences data, which fits the audio signal data's characteristics. After this, we have a dropout layer. We use 0.5 dropout rate to avoid the overfitting problem. Finally, we take a fully connected deep learning neural network as our final regressor. It will produce 2 values, Violin and Rizal, to be the final result of our model. This is the performance of our model. We use 2 different parameters, RMSE root mean squared error and PCC. RMSE is basically the distance between the true value and the predicted value. You can basically take it as how accurate it is. And PCC means how the model will learn about the tendency of the data. It means how accurate it can be when the emotion changes. Our final deployed model in our framework is this one, 10-second 100 units times 10 model, and we compare it with 3 different existing works. As you can see, this work also has 10-second fragment as its input. So we can see we have only half of their RMSE, with in this case lower RMSE and higher PCC means it's a better model. So in 10-second fragment, our model is better than the existing work. And as you can see here, this model has similar RMSE with our model, but it's on a 30-second fragment. With a shorter fragment, our model can be more flexible and we get higher availability. So basically, we are still better than this because we can have similar RMSE with a shorter fragment. As to the PCC part, as you can see in the table, our model gets the best PCC better than any other existing work. So our model is basically working better than any existing models, which is really especially in the PCC part, which is important for our appliance. Then let's have a look about the performance on cloud deployment. We test 2 different cloud deployment strategy, the serverless computing and non-serverless computing. We use Cloud Run of GCP as our cloudless computing deployment. We take 8 vCPU and 16 GI memory, and our auto-scaling max scale instance number is 120. For the non-serverless computing, we use compute engine of GCP, and the instance we take is a E2 instance with high CPU, 16V CPU, and it has a 128 GB boost task. From the chart, we can see that serverless computing can hold its function under better with higher traffic load than the non-serverless computing, so makes it our better choice. It has these advantage. First of all, it has better elasticity because it can auto self-scale up. Secondly, it gets better cost control because you pay as you use instead of you hosting a server constantly. And it shows better quality under heavier load, so that's why we choose it. In conclusion, this work proposed a novel real-time visualization framework merging music emotion recognizing model and carried by serverless computing technique. MER supplies the information loss during the transformation process, make the music information convey works in a more completed manner. Serverless computing ensures its high availability to be utilized regardless the location or time. This is a big step in music visualization field, and hopefully this work can help to bring more attention and effort to be devoted into mental health care of the hearing impact. For future direction, I think we will keep working on how to further reduce the latency and increase the image richness, given that we are taking real-time audios instead of MIDI files, so how to improve the image will be our future direction.